Natural physics is a concept astrophysicist LeRoy developed that explains in down-to-earth scenarios how the principles of physics could have come about from observing nature. Each episode begins with a scenario, followed by an example to illustrate the application of these principles in futuristic research at the frontiers of science, such as LeRoy's astrophysics doctoral research, and then concludes with an exploration of how these same principles could have very well been used by ancient cultures and civilizations. Mathematics is naturally encountered and incorporated as the exciting and fun tool of science that it is. Science is the window into our amazing world of nature, and mathematics is the tool to open that window. Natural physics encompasses current, futuristic, and ancient physics, and ties them together by the principles of physics that are common threads running throughout each.
X naught represents the original position of the proton with respect to that central trajectory, that z-axis. X naught prime is kind of like a velocity, remember? But instead of with respect to time, it represents how fast that horizontal position of the proton with respect to the central trajectory is changing with respect to how much that proton has traveled along the trajectory, along the z-axis. Y naught, that is the vertical displacement of the proton with respect to the central z-axis, okay? And Y naught prime, that represents how fast that vertical displacement is changing, how much it's changing with respect to the proton's trajectory along the z-axis, okay? So you have the original position, X naught and Y naught, the naught being the little zero is called naught, X naught, Y naught, and how fast those are changing with respect to how much that proton has traveled along the z-axis, okay? So now, that proton goes into the quadrupole, all right? And here, mathematically, we have expressed the effect that that quadrupole is going to have on the proton. And again, this is a quadrupole that is going to be focusing in the horizontal or radial direction and defocusing in the vertical or axial direction, okay? And as I said before, to represent the other kind of quadrupole that is the opposite, you would just switch the two, these four elements with these four elements, and you would have the matrix representation of a quadrupole that focuses in the vertical or axial direction and defocuses in the horizontal or radial direction. So the proton goes through this quadrupole, and when it comes out, here is its new X position, its horizontal displacement with respect to the z-axis, the trajectory. It's new how much is changing, how much its horizontal position is changing with respect to how far it goes down the z-axis, okay? And then you have its new vertical position, its new vertical displacement with respect to that central z-axis, its new Y. And you have its new, how much that vertical position, its Y position, is changing with respect to how far it's gone down the z-axis, the central trajectory. A lot of math, right? Okay, I was not even joking, was I? So again, Using linear algebra, we have a mathematical representation of a physical object, a quadrupole magnet, okay? As the proton, with its original position and changing position with respect to that central trajectory, as it enters that quadrupole, that's represented by multiplying these initial coordinates with this matrix. And out on the other end comes its new position, and how fast that position, how much that position is changing with respect to the central axis, the central trajectory, the z-axis. Okay, I think this is a great place to end for now, but I think you can see the power of mathematics in helping us to understand physical phenomena in nature, right? We use our linear algebra, our matrices, to try to understand the effects of a magnetic field on a charged particle, in this case, a proton, all right? We're somewhere out there in outer space. Evidently, you got quadrupole magnets of what we don't know that function to focus and collimate these cosmic rays, these protons that reach us at magnitudes greater than what we're able to produce here on Earth in particle accelerators like Fermilab. Somewhere out there, there's a mechanism that's able to do that. All right, we shall continue. So tune in next week, same fat time, same fat channel. I hesitated in saying this because I hope you're enjoying this. But again, I want to show you how mathematics is such a tool. Think of that toolbox. And somebody had to come up with the hammer, the screwdriver, okay, the tape measure. Somebody had to come up with the mathematical tools that enable us to try to get a handle on these phenomena in nature all around us, okay? Keep that in mind, all right? I know what I've been showing you, whoa, it's different. But again, it's all we have right now until somebody else comes up with another method to describe nature. Mathematics is all we have. Okay, so again, I know I'm repeating myself, but tune in next week, same fat time, same fat channel, and we will continue with the matrix of cosmic rays. Okie dokie. In summary, we have seen that the betatron oscillations of protons as they circulate around the booster synchrotron at Fermilab, we have seen how that motion can be described by simple harmonic motion, a spring. And by much experimentation, equations were found that correctly describe, mathematically correctly describe simple harmonic motion, the periodic motion of an object around an equilibrium position, okay? And with the same mathematical tools, the equations of that simple harmonic motion are known. And that's what was used to come up with the equations of motion for the protons as they circulate around the synchrotron along that central z-axis, that trajectory, right? 4 equations. X, the position horizontally, radially, with respect to that central trajectory. Y, the vertical displacement of the proton with respect to that central z-axis. And then you have x prime, which is how much the horizontal position of the proton changes with respect to how far it has traveled along that central trajectory. And likewise, you have y prime, how much that vertical position changes as the proton travels along that central z-axis, okay? 4 coordinates, okay? X, x prime, y prime. And you remember, we had to get that dependence away from being on time to being on how much the proton has traveled along that z-axis, okay? And then because you have 4 coordinates, you need a 4x4 matrix, right? To represent that quadrupole that's going to physically focus those protons in the horizontal, the radial direction with respect to the z-axis, but it's going to defocus the protons in the vertical, the axial direction, okay? So that's what that 4x4 matrix represents. And as I said, to get the mathematical representation of the other matrix, you just flip those 4 elements, okay? So what we're looking at to try to track these betatron oscillations, to track the simple harmonic motion of the protons as they circulate around the booster synchrotron, we're looking at 48 quadrupoles, 24 cells consisting of 2 quadrupoles, each one of different types. One horizontally focusing, vertically defocusing, and the other one vertically focusing and horizontally defocusing, okay? So we're going to be using linear algebra matrices to start getting a handle on tracking these betatron oscillations of protons around the synchrotron. Okie dokie. So tune in next week, same fat time, same fat channel.